Hello, we'll be presenting our work on GraphLAMA. It's an efficient graph language adaptation. So the goal of this model is to combine the strengths of GNNs and LLMs using lightweight adapters, enabling fast and accurate adaptation on text attributed graphs. So in graphs where the node in itself has the text parameters. This includes understanding the architecture and the basic mathematics and our studies on the GraphLAMA. Moving ahead. So why existing GLM struggle? So this is the overall problem statement which GraphLAMA addresses. In most like real-life datasets like citation networks, shopping networks, or social graphs, a node contains the both structure and the text, and this is what we call as text attributed graphs. GNNs are great at structural reasoning, but they can't understand language deeply, and LLMs are excellent at language but completely ignore the graph structure. So here is a comparison between two popular fine-tuning mechanisms, that is graph in context learning and graph instruction tuning. Now, for domain adaptation, both does not give us the required results, and they need a good amount of data. And GraphLAMA efficiently adapts this graph language model to new tasks with very few labeled examples. So it's basically a few shot learning for graph text attributed graphs. Like moving ahead, here's the architecture of GraphLAMA. It works on a three-stage system. First comes the graph encoder. It encodes the structure-aware node embeddings. I'll explain it in more detail. After getting the node embeddings, we pass it through the hop encoder. Now, hop encoder adds the structural distance information. Say, from a given node, we have a node which is one distance away. We have nodes which are 2, 3 hops away. It adds their embeddings, and then we pass it through the gating mechanism. This is the heart of the GraphLAMA because it adds two gates, that is task invariant and task related gates, through which we get the information which has to be passed. Let's say, for example, we are fine-tuning on a particular task. The embeddings relevant to that particular task is passed through the task related gate, and task invariant gates shares a fixed knowledge, a corpus of fixed knowledge across the tasks. And after aggregating the embeddings from both these gates, we project it. So to process our data through LLM, we have to project it to the LLM token space, and then LLM performs the text reasoning and classification. As you can see in the example, we have given a sequence of node tokens where each token represents a product, and then the first token is target item. We pass the name and description and the task. The response which we get is that what is the paper about or what is the product about.
So now let's move ahead to the core mathematics behind this philosophy. So the maths behind is that first the GNN computes the embeddings, and then we concatenate the hop information to this. Next come the gating mechanism. So there are two types of gates as discussed before, the task invariant gate and the task related gate. So after getting the results from the gate, we combine these results using the W aggregate, and then we project it into the LLM space using a kernel. Finally, the LLM predicts the label. We give it a query of the task. Suppose the task is of classification, so we give the projected embedding text and the instructions, and then on the basis of that, it gives us the answer. So the training objective is the standard cross entropy, and this is the complete mathematical philosophy of GraphLAMA. Next, what we did was we first ran this GraphLAMA with our experiment on Quora. So when we ran this on Quora, we used only 20 labeled samples per class, and this few shot adaptation scenario that we had used. With LLM active, it achieved 87.4% accuracy, and fine tuning took 4.2 minutes on our T4 GPU available on the Colab. Only after 2.8 million of parameters were updated, MB of parameters were updated, inference was 9.1 times faster than the prompt based methods. And then in zero shot, we actually reached over 81% of accuracy, but in the zero shot, there was no fine tuning. Now, this shows that LLM help us align the semantic meaning across neighbors and boosting classification. So now next move on to the ablation studies that we did as discussed, or as a task it was given us to in the mid of the semesters. So the ablation study was as told by our teacher to remove the LLM and then run it. So to understand the importance of LLM, we performed an ablation by removing it entirely and using a simple linear classifier instead. And the accuracy quite expectedly dropped sharply from 87.4% to approximately 72%. This loss increased and confusion between similar classes increased, just as suppose a paper was on the neural net and the other was on the reinforcement learning. So this rose by 31%. This confusion rose by 31%. This is because the LLM is responsible for capturing deeper semantic meaning of the text of these papers and such terminology and topic relationships. Without LLM, the model becomes purely structural and loses its ability to differentiate the fine-grained topics. So LLM is essential for rich reasoning on text attributed graphs. So next, a paper was given to us and it was asked the relationship between the two papers. So are CLGR questions valid in this case? So CLGR benchmark from a graph stock but whose listening paper. It's designed to test compositional reasoning, combining graph structure with textual clues. It evaluates path reasoning, constraint satisfaction, symbolic reasoning, and graph text interactions. GraphLAMA, however, focuses on efficient adaptation mechanism, not question answering. It is mainly trained for classification and summarization tasks. So CLEGR questions are not directly valid for comparing with GraphLAMA, but conceptually both involve graph text reasoning, so CLEGR could be a meaningful future evaluation to GraphLAMA. Now let's next move on to why GraphLAMA works. So let's look at why GraphLAMA succeeds. The GNN builds the structure and backbone awareness of the representations of the structure, and then hop encoding actually inform the systems about the neighborhood distances in that structure of the graph.
Now the gating mechanism splits the global knowledge and task specific knowledge. This helps us allow efficient adaptation to the task. Then we move to the projection layer, which aligns the graph embeddings with the LLM's token space. It allows a joint reasoning between LLM and graphs. And finally, the LLM interprets the natural language node description which we give as input, and it gives it a strong semantic grounding. Now, taken together, these components help a system that understands both structure and language effectively. So essentially, it's a clergy of both the graph and the LLMs. Next, we explain what we did.
So in our improved version, we performed a clean ablation study and analyzed how removing the LLM affects the accuracy and semantics of this GraphLAMA. We ran experiments with parameters and strengthened the mathematical explanation. We also evaluated the CLEGR questions that are actually applicable and proposed how GraphLAMA could be extended to reasoning heavy tasks in the future. That is our future plan. And we actually highlighted the GraphLAMA strengths, limitations, and possible future extensions that can be done. So the conclusion is so the conclusion is that GraphLAMA achieved efficient adaptation using lightweight adapters, strong performance through graph plus text synergy, high semantic reasoning with LLMs, which is necessary as we saw in our ablation study, and robust few-shot learning across domains. It was valid but non-overlapping relationships with CLEGR evaluation. So this is what we done. So this was our good team. I, Yashraj, Anushk, and Om Prakash worked on this project together. This was actually our mini project for our course Learning on Graphs at IIT Jodhpur 2025. Thank you.